the statistical techniques which are meant for more than one variable at a time. In the previous session, we learnt correlation analysis, the mainly correlation coefficient between two variables, which gives us an idea about the extent of relationship between the two variables. Some examples of dependent variables which we saw: height and weight, age of a person and blood pressure, marks between two subjects of the same student. So, we feel that they are dependent, and then we try to find out the statistical measure meant for the association between the two variables, which is called as correlation coefficient. Having known the extent of correlation between two variables, we now further proceed to come up with an answer to the question whether if we are given value of one of the two variables, can we estimate or can we predict or forecast the value of the other variable. So, in the sense that can we come up with a kind of mathematical formulation which will help us getting an idea about the other variable given the first variable. For example, if you are trying to model the relationship between weight of a person and height of a person, then given the height of the individual, are we able to find out, which we in statistics called as estimate, the value of the weight of that person? Do we get some idea? That is what is meant by estimate. So, regression analysis is a technique which is used to answer such type of questions. So, first we will consider only two variables data, that is bivariate data. One of the variables as dependent variable and other as independent variable. So, in today's session, the agenda is understand the simple regression analysis and when should we use it, the types of regression models, understanding various aspects of simple regression analysis, which we often call as binary regression also, and a coefficient, a statistical measure known as coefficient of determination, which gives us an idea about the strength of the linear relationship between the two variables, followed by an example. So, we will first see what is simple regression analysis and when should one use it. The objective of regression analysis is the formulation and determination of the dependent variable given the value of the independent variable. So, in simple regression analysis, we analyze the relationship between two variables. One of them is known as independent and the other as dependent. Now, the roles the two variables are playing as dependent and independent, that depends upon the context. If we feel that the systolic blood pressure varies as age, then systolic blood pressure becomes dependent variable and age is known as the independent variable. Not necessarily that always the relationship should be kind of cause and effect. We can consider one of them as independent and other as dependent. Mainly the variable which we want to predict, we consider that variable as dependent variable. In case of agricultural experiments, when you are talking about yield and rainfall, then obviously we don't predict rainfall on the basis of yield, but we predict yield on the basis of rainfall. So, yield becomes dependent variable and the rainfall in millimeters become the independent variable. So, mainly in clinical trials domain also, the severity of the disease or efficacy of the drug whichever variables are characterizing these attributes, they will definitely form the dependent variables. So, in simple regression or binary regression, we are considering bivariate data which we feel that they are correlated with each other. Then only it makes sense to go in for modeling that data using the binary regression. I would also like to mention here that we will be considering only the linear regression. So, a straight line fit. We are not into the non-linear regression yet. Whereas, in the regression analysis, there could be several such models of non-linear regression. There can be called as something called as logistic regression, which are some advanced topics. We are not dealing to that. We are understanding the first concept of simple regression analysis. So, regression analysis can be used to identify the explanatory variables that can most effectively influence or control the value of the outcome variable. So, which variables to consider? That is the job of the statistician given the huge amount of data that has been collected. There are several techniques also to find out the subset of variables which are really impacting the response variable and only work on that data set which this particular topic is out of scope of this session as far as today's session is concerned. The relationship between these two variables could be linear or non-linear. As I mentioned, we are going to consider only the linear regression here. So, regression analysis can also be used to estimate the future value of a variable. So, one is like this, that we want to estimate the population, we want to forecast what will happen in the future, we want to forecast the population of the country given the data from the past few census, and we would like to say forecast the population of India in say 2021 after having conducted the census in 2011. So, that's one objective of regression analysis, but that is not the objective of regression analysis. The regression also helps us not necessarily all the time in predicting, but also getting the idea, the mathematical relationship between the two variables. That could be of immense use in designing the experiments of or clinical trials, because if the two variables are closely related and that we observe from the scatter diagram as we discussed in the correlation, then we think of going further and then one can predict the response variable with the help of the other secondary variable. So, as you know, there are two variables in clinical trial, primary variable, primary endpoint, secondary endpoint. So, if you get an idea about secondary endpoint, that might help you in giving you some idea about the primary endpoint if you know the regression of primary endpoint on the secondary endpoint. So, this is in a very crude way explanation for the regression analysis. A simple example could be that as we say that the systolic blood pressure increases with age, and then if we can model it, that what is the formula given the age, suppose the age of the person is 55 years, then can we predict his systolic blood pressure. So, if we have an equation, then we will be able to predict the blood pressure of that person. So, getting that equation, getting that mathematical model is the objective of the simple regression analysis. Okay. So, let us move further. Both these variables are of quantitative type or numeric interval or ratio type mainly. Whenever the response variable is of binary type, then we get into the logistic regression. So, that is not the case here. We are assuming that both y and x are of quantitative nature and mainly of the continuous kind of variables. So, again the use is predicting unmeasured responses from a known x value. So, generally the dependent variable is difficult to measure, but the independent variable is easy to measure. Then you use this regression. Some of the examples of regression analysis are as follows. Modeling of blood pressure response Y on the dose of a new antihypertensive drug. How the drug is effective in reducing the blood pressure. So, that kind of relationship or dependence you want to observe, then you consider this regression. Similarly, cholesterol level Y on patient's age X, pain relief Y on time after dosing with an anti-inflammatory treatment, degree of wound healing on the baseline surface area of a burn wound. There could be several, thousands of examples of binary regression context. Now, you will observe one thing, that here all the time we are calling as y as the dependent variable and x as independent variable. But that is not hard and fast. You can consider x as dependent and y as independent. This is just conventionally we are calling them as y and x. So, if we look at the variety of regression models we have, they are mainly classified into two branches, simple, that is binary, and multiple, where in case of multiple you have a single dependent variable but more than one independent variable. That is obvious because saying that one response variable depends only on one independent variable is a short-sightedness. Actually, the endpoint response depends on a variety of other variables. It depends on age, sex, cholesterol level, then dose that is given to that physical activity. You can come up with several such explanatory variables. So, they are also called as explanatory variables, these independent variables, and they sometimes are called as predictors. So, all these are synonyms: independent variables, explanatory variables, factors, and predictors are nothing but the independent variables. When we will look at these multiple regression, we will talk more about the roles of these independent variables. Right now, our world is very small. We have only one dependent variable and one explanatory variable. So, again in simple regression, you can classify it into linear and non-linear kind of regression. The non-linear, I remember I explained to you, kind of parabola. If you increase the dose too much, then the response will not be increasing, in fact it will be detrimental. So, in that case the fit will not be linear, it could be a parabolic situation. So, here we are not considering the non-linear, we are considering only the linear part of it. So, what are we ultimately trying to do? In simple regression analysis, we want to build a relationship between y and x. So, y should be able to return as alpha plus beta x and plus epsilon. Now, this epsilon is a famous creature of statisticians. This is called as an error, chance error, that we call it as chance error. So, it is not that y will be exactly equal to some constant plus some constant into the x value, because there is inherent variation in the variable x and the relationship as well. So, this inherent variation is taken care by the epsilon. Let us not worry about this fellow much. This is nothing but the error in our estimation. So, where alpha is the intercept and beta is the slope. As the response is subject to random measurement error, y might differ in repeated sampling for a sample value of x. That means for the same value of x, if you are observing, again you may not get the same value of y because of this epsilon. The epsilon accounts for this random nature of the response y. This is our favorite scatter diagram drawn x and y. All of you know this scatter diagram because we have drawn it when we learned correlation. This scatter diagram shows us a positive trend, and we had seen that time also that if we compute the correlation coefficient, then it will turn out to be equal to some positive number. The correlation coefficient R lies between -1 and +1, and for such kind of data it will be between 0 and 1. Since the data points are scattered around and they are scattered in a thin manner, they are not very tightly scattered, they are not dense. So therefore the correlation is positive but definitely not very close to 1. The correlation for this could be 0.3 or 0.4, only up to, so it is a weak positive correlation situation. I explained all this just to refresh what we learnt in correlation. So correlation gave us the idea that there is a kind of positive relationship between the variables y and x. In regression, we want to move one step ahead by fitting a line of regression. So this is the line of regression that we are fitting. By fitting the line of regression to the data, how do we do that and how do we achieve that, and what do we mean by fitting a line? Now those of you who remember the coordinate geometry that you learnt in your school days will be able to appreciate that a line in coordinate geometry has an equation of the kind y equal to alpha plus beta x or a plus bx for that matter. So any line can be written as mx plus c or a plus bx or alpha plus beta x. Main point is that you have some constant plus some constant into the variable x. What will be this constant? See, when x is equal to 0, y will have the value alpha. So here when x is 0, wherever the line cuts your y-axis, that distance will be equal to alpha. And beta is known as the slope of the line. Alpha is the intercept and beta is the slope. Now what is meant by fitting a straight line to this? Suppose I would not have drawn this line here, and then we would have tried several lines which will describe this data pretty well. For example, I may draw a line like this. Imagine that I am drawing a line, or I may draw a line like this. Okay. So in all such cases, there can be several such lines drawn to the same data, and with the objective that the line should be explaining the pattern or the correlation in the data. So there can be infinitely many lines. Everybody will draw a different line and the equation of the line will change, and then with every line you can get a different value of y for the same value of x, obviously, right? So we want the line, we want a single unique line, which is the best line fit to the data. For that purpose, what is done or what is employed here is the least squares principle. See, here you again see that creature epsilon here. What is this epsilon? This point y value is actually here, the coordinate y value is here, you can measure it, whatever it is, and the value of y on the line for that corresponding x is this. So this is the, if I consider this point, then this is the value of y on the line, this is the value of y truly observed. So what is epsilon here? This is the difference between the observed value and the y value on the line. Okay. So y value on the line is called as y estimate because this is given by this line. This is the model that we are using for estimating the y value. So the value on the line is known as y estimate, whereas the coordinate, y coordinate of the point is known as the observed value of y. So observed value minus the estimate is the error. We want the line to be the best line so that all these errors should be as minimum as possible. Okay. Now definitely one cannot have a single line which will pass through all these points. You cannot draw a single line. So you will try to minimize these errors for all the points. So what is done in least squares principle is that these distances are measured, all these distances are squared, then their sum is taken and that is minimized. That is minimized for what? That is minimized for computing the estimates of alpha and beta. So when you do that, we will not bother about the theoretical details. So when you do that, you will get the estimates of alpha and beta as a plus b, suppose. And then you form an equation as y hat is equal to a plus bx. So this particular is nothing but the equation of the line, equation of the best fitting line, and it is also known as the equation of the line of regression of y on x. All these language and all these words are very important. If you say that this is an equation of x on y, then that is wrong. This is an equation of y, regression of y on x. Of is associated with the dependent variable and on is with the independent variable. Okay. So the prediction equation represents the best estimate of the unknown regression model. So we have tried to model the data by fitting the line of regression. That is whatever I explained just now, that is been depicted on this slide. We seek values for a and b such that the predicted response y hat is as close as possible to the observed response y for all measured data points. The all measured data points is very important. That is why one way to satisfy this requirement is to minimize the sum of square differences between y and y hat. So you take the differences, square them. Y to square, now all of us know, we square because the positive negatives cancel each other. So we square them, take the sum and then minimize using calculus methods, and we obtain the values of a and b. Some bombardment of formula, you need not worry, for the sake of reference and completeness they are kept here. Once you solve them, you get b and a. So given data, the point is that given the bivariate data, given the observations x and y, you can find out the value of b as sxy upon sxx and a equal to y bar minus b times x bar, where y bar and x bar are the arithmetic means of y and x. B is already computed here. So one thing is sure, that you cannot compute A unless you compute B. You have to first compute B, which is the regression coefficient of y on x. Now what does it mean? The regression coefficient B means that what is the impact on the variable y for the unit change in the independent variable x. So if you change the value of x by 1 unit, then how much will be y changed? The y will change by b units. I would like to explain it by our famous height weight example. Suppose x is the height in centimeters and b is the regression coefficient of weight on height in kg, and b turns out to be equal to say 1.2. So if x changes or x increases by 1 centimeter. If the person's height increases by 1 centimeter, then his weight will increase by 1.2 kg. That is the meaning of the regression coefficient. Now this is all estimate, so we expect, all these things are there underlined, we expect that the weight of the person will increase by 1.2. Now this B, the sign of this B tells us whether there is a positive or negative kind of correlation. So if B is positive, then you are in the positive correlation setup. If B is negative, then for 1 unit increase in x, that much will be the decrease in y, and likewise. So that is the interpretation of the regression coefficient, and that is very important. You can also compute the best estimate of the variance is a square, which is sums of squares for errors, divided by n minus 2 and some other quantities which SAS, Proc Reg, Proc GLM also give. Having computed the line of regression y equal to bx plus or a plus bx, the main question one would like to answer is concerning the significance of the slope parameter, that is significance of the regression coefficient. In statistics, henceforth you will hear the word significance maybe thousands of times. Significance of something, something is significant, something is not significant. In simple word, significance of the slope parameter means you would say that slope parameter or regression coefficient is significant, that means it is not 0. Something is significant is equivalent to saying that something is not equal to 0. You can remember that. So, not 0 means what? If it is 0, then what happens? If it is 0, then the value of x will not improve the prediction of y over the ordinary predictor y. That means both the things have nothing to do with each other. You are measuring something on x and measuring something on y which is not at all related to x. Then even though you measure x, you won't come to know the value of y. Even though you measure income of a person, you won't come to know his height. So why there should be a relation between income and height? So some such kind of data you are trying to analyze using regression, and then if beta is equal to 0. In clinical trials, this is very important statement, that if you if your beta turns out to be equal to 0, then you can say that that particular predictor or explanatory variable is not contributing in judging about the response variable at all. Okay, so you may not measure it. Why should you measure the number of children in the family if you are talking about the degree of cancer? Something like that. So that's a very important kind of inference that one gets if beta turns out to be equal to 0. On the other hand, if beta is non-zero and it proved that it is significant, then x is significantly impacting the dependent variable y. That is what it means. So whichever x you are considering, age is a significant variable to be considered for predicting the blood pressure, systolic blood pressure. Weight could be a significant variable for predicting the systolic blood pressure. Okay. But color of eye or color of hair may not be a significant variable for predicting the systolic blood pressure, if color is obviously measured in the numeric terms. So these kind of inferences we want to come up when we do the regression analysis. The point here I want to make is that regression analysis doesn't stop when you compute or when you fit the line of regression. It actually starts over there because you further go in for testing whether that beta is equal to 0 or not, whether it is significantly impacting, what is the kind of relationship, etc. etc. So that becomes a starting point for the further complicated statistical analysis. A significant slope beta indicating a linear relationship between x and y means that knowledge of the x values will significantly improve your prediction ability. Okay, fine. We tried to compute that beta. We computed that, estimated that beta by our b, which is the regression coefficient based on our data. And now we want to see how good is the line of fit. Even though it is the best line fit, see, best line fit, that best word in the sense of getting the best line from using the data. But that doesn't mean that it is the best model between the two variables. So, how good is the best line fit? Suppose we want to know that, then that information or that knowledge is provided by coefficient of determination, and that is computed as r square, which is our regular correlation coefficient also denoted by small r. Whenever we get into the multiple regression and multiple correlation setup, then we denote it by capital R. Coefficient of determination is the ratio of the explained variation to the total variation, which is the square of the correlation coefficient. It gives the proportion of the variance of one variable that is predictable from other variable. It is a measure that allows us to determine how certain one can be in making predictions from a certain model or graph. 0 is less than r square less than 1 denotes the strength of the linear association between x and y. This is obvious because r is between -1 and +1. So, r square will be between 0 and 1. Suppose r is equal to 0.9, then the value of r square will be 0.81. So, what does that mean? 0.81, whether it is a good value or okay value or a bad value, as far as the goodness of the model is concerned, it is a very good value, because what is it saying? That it gives the proportion of the variance of variable y that is predictable from the other variable. So, when your r is 0.9, r square is 0.81, what does that mean? That 81% of the variation in the variable y is explained by this regression of y on x. So, because you had the information on the variable x, so x has helped you in understanding for the variable y and its variation 81%. And what about the remaining 19%? That remaining 19% is being eaten by that creature epsilon. Okay. So, the remaining 19% is not it's called as unexplained variation by the regression. And in none of the cases except when your x's and y are perfectly correlated, that is the correlation coefficient equal to 1, as we were saying in the previous lecture, say y is equal to 3x plus 5 all the time, no matter what the world is going to be. In that case only, you 100% variation in y will be explained by x. But our value of r equal to 0.9 or 80% of the variation is a good amount of idea that is being given by the regression of y on x. So, that idea is provided by coefficient of determination r square. So, the coefficient of determination represents the percent of the data that is the closest to the line of best fit. Similar example explained over here. If your r is 0.922, then r square is so and so, 85% of the total variation in y can be explained by the linear relationship between x and y. The other 15% of the total variation in y remains unexplained. So, the coefficient of determination is a measure of how well the regression line represents the data. If the regression line passes exactly through every point on the scatter plot, it would be able to explain all of the variation, but it will not be the case anytime. The further the line is away from the points, the less it is able to explain the data, because the relationship is not tight. So, if the relationship is not tight, why should the regression equation be good? So, before going into the SAS example, I would like to demonstrate a simple data which we saw at the time of correlation and how the line of regression is fit to that in Excel. So, this was our data of x and y. We had seen that the correlation coefficient was 0.933. So, very good correlation between the two variables. Now, when you fit the line of regression using Excel, you get this kind of statistics. So, see, the multiple R is the same as that R, because there are only two variables. R square, this is the coefficient of determination here. There is some other quantity called as adjusted R square, which we will have a look at when we go in for the multiple regression. Standard error, the number of data points, then the degrees of freedom, residual and total. This is an analysis of variance table. So, 576.72 sums of squares. So, this is the variation that is explained. We were saying that 87% of the variation will be explained. Which is the total variation? This is total variation, and this becomes 87% of that, and that will be explained by regression. This much is not explained by the regression. So, 13% will not be explained by regression. Then you compute here some test statistics, its values, and this is the significance of the test statistic, the p value, which gives you whether the slope is or the model is good or bad. Here you get the equation. See, here it is the coefficient of x. So, if you want to write that equation, see, y equal to, suppose you want to write it as y equal to a plus bx. So, here it will be y equal to, this will be your a, okay. So, 8.6766 will be your a plus this will be your b times x. So, this will be 2.177x, okay. So, this will be your equation, this plus this value. So, given the value of x, you can find out using this equation the value of y, which is known as the estimated or predicted value of y, which is being shown on this plot. So, this was our original data, the blue points. These points are the predicted y values given by the equation, and you can fit this line, and this is the best line possible using the data. Here, even though we are not going into the p value and all, I would like to tell you something about that. See, this is intercept and this is coefficient. So, this is the coefficient of x. So, this is our actually the regression coefficient, and the significance of that is understood by the p value. This is 10 raised to minus 5. So, the p value is very close to 0. When the p value is less than 0.05, you say that the coefficient is significant. Here it is very close to 0, so it is definitely less than 0.05. So, here this regression coefficient is significant. That is what we come to know by looking at the data. Then there are some residuals and other things which are plotted by Excel. Now, let us have a look at an example which is run using SAS procedures. So, this is an example which is talking about anti-anginal response versus disease history. Treadmill stress tests were administered to patients with angina pectoris before and after 4 weeks, once daily dosing with an experimental anti-anginal medication. The investigator wanted to know if the improvement in exercise duration is related to the patient's disease history. So, we have two variables. One is disease duration and other is the improvement, percent improvement. So, disease duration since initial diagnosis in years and percent improvement in treadmill walking times are shown in the following table for a study with 20 patients enrolled. Is there a significant linear relationship between improvement on medication and disease duration? So, the raw data looks like this, X and Y. The disease duration are in years and percentage improvement. So, which is dependent and which is independent? Obviously, percentage improvement seems to be dependent on disease duration. So, we try to fit the regression line of Y on X. This is SAS code, you can run it. You can also use proc reg or proc GLM, both give you the similar output for this data at least. First, if you run proc means procedure, you get the summary of means and standard deviations, number of variables, etc. This is the main output here. So, the model sum of squares, so regression sum of squares, error sum of squares and the total sum of squares. So, here you observe that the model sum of squares are very less as compared to the total sum of squares, and that is shown here that your value of that coefficient of determination is very less. Mainly we will come to that. Before that, the regression estimates A and B are printed in the estimate column output of proc GLM. The t-test for slope is minus 2.40 with a p-value of 0.0276. So, as I mentioned that since it is less than 0.05, we reject H naught and conclude that treadmill improvement has a significant linear relationship to disease duration. So, basically the regression coefficient is not 0, that is what we conclude. The P and CLM options specified in the model statement request the predicted values based on the regression equation for each data point along with the 95% confidence intervals for the mean response at the corresponding x values. This confidence intervals concept also we will see whenever we will talk about the statistical inference in estimation part. So, here it is, R square is coming out to be equal to 0.242, which is a measure of goodness of fit, that is the coefficient of determination, and since it is very low value, it has to be between 0 and 1, so above 0.8 is good. So, it is a very low value, so it does not indicate a very promising relationship, promising model in as far as the regression model is concerned. Even though that whatever model we are fitting giving us that regression slope is significant, but the model itself is not good. That is what the moral of the story here. The Durbin-Watson test is used to check for autocorrelation. A value close to 2 such as 1.92 indicates no significant autocorrelation. So, these are again some advanced topics, we are not going to worry about this here. So, today what we have learnt is about the simple regression analysis in the two variables or bivariable setup. When should we use it? What are the objectives behind using the simple regression analysis? Then types of regression models, actually it is a general, not only for two variables. Understanding various aspects of simple regression analysis. how to compute the estimates A and B using the least squares principle, coefficient of determination R square, how and what does it indicate, how does it specify the strength of the relationship between the two variables, and an example using the SAS prox.